Mini PHYTER 10-100 Ethernet transceivers. National Semiconductor. Welcome to this training module on National Semiconductor's Mini PHYTER 10/100 Ethernet transceivers. This training module provides an overview of the Mini PHYTER transceivers and their operations. The Open Systems Interconnect was a working group under the ISO attempting to get everyone to agree to common network standards. It promoted the idea of a common model of protocol layers defining interoperability between network devices and software. The OSI reference model defines 7 layers that describe how applications running upon network-aware devices may communicate with each other. The model is generic and applies to all network types. The IEEE 802.3 standard implements only a portion of the OSI 7-layer model. The diagram shows the IEEE 802.3 logical layers and their relationship to the OSI reference model. As with all IEEE 802 protocols, the OSI data link layer is divided into 2 IEEE 802 sublayers, the media access control sublayer and the logical link control sublayer. The 802.3 physical layer is specific to the transmission data rate, the signal encoding, and the type of media interconnecting the 2 nodes. The MAC layer controls the node's access to the network media and is specific to the individual protocol. The term Ethernet refers to the family of local area network products covered by the IEEE 802.3 standard. 3 data rates are currently defined for operation over fiber optic and twisted pair cables. 10 megabits per second, 10 base T, 100 megabits per second, fast Ethernet, and 1000 megabits per second, gigabit Ethernet. The Mini PHYTER products are robust, full-featured, low-power, 10/100 physical layer devices, with cable length performance far exceeding IEEE specifications and features that provide lower cost solutions for both 10 base T and 100 base T Ethernet protocols. The devices ensure compatibility and interoperability with other standards based on Ethernet products. The figure is a typical Ethernet application of a Mini PHYTER devices. The Mini PHYTER addresses the quality, reliability, and small form factor required for space-sensitive applications in embedded systems. The basic functions of the devices in the Mini PHYTER family are similar. Differences include feature set, pin functions, and possible register operation. The table is a simple guide for selecting Mini PHYTER devices. The Mini PHYTER supports 2 modes of operation, M2 mode and RM2 mode, using the M2 interface pins. The Media Independent Interface, M2, may be used to connect PHY devices to a MAC in 10/100 megabit per second systems. The Reduced Media Independent Interface, RMII, is used to connect PHY devices to a MAC in 10/100 megabit per second systems using a reduced number of pins. These modes of operation can be selected by strap options on or a control register. In each of these modes, the IEEE 802.3 serial management interface is operational for device configuration and status. The table shows the management data input-output frame format. The 100 base T transmitter consists of several functional blocks which convert synchronous 4-bit nibble data to a scrambled MLT-5 125 megabit per second serial data stream. The block diagram provides an overview of each functional block within the 100 base T transmit section. The transmitter section consists of a code group encoder and injection block, scrambler block, NRZ to NRZI encoder block, and a binary to MLT-3 converter / common driver. The code group encoder converts 4-bit nibble data generated by the MAC into 5-bit code groups for transmission. The scrambler is used to control the radiated emissions at the media connector and on the twisted pair cable. NRZI encoded data makes the transmit data stream comply with the TB PMD standard for 100 base T transmission over Category 5 unshielded twisted pair cable. The binary to MLT-3 conversion is accomplished by converting the serial binary data stream output from the NRZI encoder into two binary data streams with alternately phased logic 1 events. The 100 base T receiver convert the scrambled MLT-3 125 megabits per second serial data stream to synchronous 4-bit nibble data that is provided to the MII. The receive section consists of an analog front end, digital signal processor, signal detect, MLT-3 to binary decoder, NRZI to NRZ decoder, serial to parallel, descrambler, code group alignment, 4-bit, 5-bit decoder, link integrity monitor, and bad SSD detection. The figure shows the 100 base T receive function. The 10 base T transceiver module is IEEE 802.3 compliant. It includes the receiver, transmitter, collision, heartbeat, loopback, jabber, and link integrity functions as defined in the standard. An external filter is not required on the 10 base T interface since it is integrated inside the mini PHYTER. Here focuses on the general 10 base T system level operation. Mini PHYTER products include an internal power-on reset function and does not need to be explicitly reset after power-up. For normal operation, if required during normal operation, the device can be reset by a hardware or software reset. A hardware reset is accomplished by applying a low-pulse TTL level with a duration of at least 1 millisecond to the reset in pin. A software reset is accomplished by setting the release bit, pin 15, of the basic mode control register. The medium or medium-dependent interface connection is via the transmit and receive differential pair pins. These connect to a termination network, then to a 1-to-1 transformer, and a RJ45 connector. A standard Cat5 Ethernet cable is then used to connect to the rest of the network. The figure shows the recommended 10/100 megabit per second twisted pair interface circuit. Many PHYTER family products support either an external CMOS level oscillator source or a crystal resonator device. The X1 pin is the clock input, requiring either 25 or 50 MHz depending on the M2 mode used. In M2 mode, either a 25 MHz crystal or a 25 MHz oscillator may be used. For all many PHYTER family products, the use of standard RMII mode requires the use of a 50 MHz oscillator. If the external clock source is used, X1 should be tied to the clock source and X2 should be left floating. A 25 MHz parallel 20 picofarad load crystal resonator should be used if a crystal source is desired. The figure shows the typical connection for a crystal resonator circuit. To ensure correct operation for the mini PHYTER, the VDD supply pin should be bypassed with a low impedance 0.1 microfarad surface mount capacitor. To reduce EMI, the capacitor should be placed as close as possible to the component VDD supply pins. Some PHYTER products utilize printed circuit board traces to connect an internal regulator to core supply pins. On these products, the PFB out pin should be tied to the PFB in 1 and 2 pins using as much printed circuit board copper as possible. A 10 microfarad tantalum capacitor in parallel with a 0.1 microfarad capacitor should be placed close to the PFB out pin, and A 0.1 microfarad capacitor should be as close as possible to the PFB-N1 and PFB-N2 pins.